Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization, Oil and Gas Production, Surface Modeling of Oilfields. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Presents the conference. Superficial modeling of oil fields as part of oil and gas production optimization. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Topic: Framework. The model that is going to be presented will be called OilPro. With the emergence of new and more efficient computer technologies, the use of simulators to predict the behavior of wells has received great attention from the industry. Based on simulation results, simplified production profile models can be built to represent the response functions of the reservoir, to be used as input for optimization process. In this way, the nonlinear behavior of the reservoir is included indirectly in the optimization model, but the parameters that define the function that describes the behavior of the reservoir are established by several runs of a simulator. By the beginning of the present century, there were already multiple works that used this approach. Among them we can cite those of Hussaby and Hovardson, 2009, Kosmitis et al. 2004, 2005, Wang et al. 2002, Davidson and Beckner, 2003, and Nas et al. 2004, Hepguler et al. 1997, Litvak et al. 1997, and Magalhães, 2005. In general, all of them use an optimization simulation model to perform an analysis of the impact of the production capacity of the system as a result of the production strategies of the reservoir. There are ways to integrate a simulation model into an optimization model. Static: a simulator feeds data to the optimization model through functions that relates the reservoir response to the operating variables, and dynamic: an integrated simulation optimization scheme iterative, in which at each step of the optimization model, the reservoir model determines the impact of the proposed operation, and based on this, a new operation scheme is proposed. Bittencourt et al. Presents an optimization approach in which data generated by the Eclipse reservoir simulator is used in the calculation of the cost functions. Considering the simulation results and cost parameters of the oil industry, the optimizer returns the cash flow analysis for the current case. The case considered is when the production of one reservoir begins to decline, a second reservoir enters production to obtain the maximum capacity of the installed facilities. The parameters to be obtained from the simulation are the time when the second reservoir must enter production, and how long the new reservoir in operation will last. The data calculated by the simulator are the crude oil production rate, and the number of wells required to reach the goal rate in each time interval. The optimization model generates input data for the simulator, using the polytope search method. The iterative procedure used is: first, the simulation must be initialized with the input parameters. After this begins the iterative process. Step 2, the simulator runs the model, and obtains data on the production rate, and the number of wells required in the period considered. The information enters the optimization algorithm, which defines the required production profile, and defines the remaining production periods, given the exploitation information of the reservoir, so that the algorithm distributes costs and revenues over time and returns the cash flow value for the defined parameters. The optimizer sends the production program to the simulator. The simulator will feed the data to produce new information on the behavior of the reservoir and the period of operation of the reservoir, and the algorithm returns to step 2. In the case to be presented, the optimization algorithm must communicate with the simulation algorithm, maybe in a static or in dynamic communication. If the oil recovery is secondary or tertiary, the communication should be dynamic, since the injection of materials into the subsoil affects the pressures in the reservoir. For the case of primary recovery, the communication could be static, since the optimization model could simulate the evolution of the pressures in the reservoir, as a consequence of the accumulated production. Topic: Field Operations Modeling. The mathematical modeling of the production system is based on the combination of the representations proposed by Iyer et al. 1998, Barragan Hernandez et al. 2005, and Cosmitis, 2005. The need to combine these conceptualizations lies in the fact that they have complementary elements to configure the productive system. For the mathematical modeling, a reservoir is defined as a porous, permeable underground formation, containing an individual reservoir of hydrocarbons confined by impermeable rock, or water barriers, and is characterized by a unique natural pressure system. High Oil Pro includes the following entities. Production system corresponds to the macro facility that houses all the basic production facilities required to produce oil and/or gas. Field, set of deposits in which oil and/or gas is deposited, and that together make up the production system. Reservoir, confined deposit where hydrocarbons are. The reservoir is associated with a field and the surface piping systems that are required to handle the process. Well, the way of extraction of hydrocarbons, they connect the reservoir with a collector. Collector, section of surface pipe that connecting wells to production platforms. Platforms to other platforms, and platforms to process plants. Platform is a collector concentration point. Separator unit, where the separation of oil, gas, and water is carried out. Tanks, product storages, from which the crude oil and/or gas transport system is fed. They belong to the terminal, or node, where is connected to the production system. The conceptualization of the field can be done based on the following principles. Well, it corresponds to the basic unit of production. Reservoir, it corresponds to a set of wells that operate an oil deposit that is interconnected in the subsoil, and field, it corresponds to a set of multiple oil deposits which contribute their production to a collection and processing infrastructure. The collection infrastructure is composed of separator, production unit in which oil, gas and water are separated. Collector, it is composed of a network of pipes that connect the fields with the separator, and tanks, storages of oil, gas and water, already processed. The topologies of the network can be very varied, since an O&G production facility can have multiple components of each type. The image presents the hierarchical connectivity of an oil field infrastructure. A processing system has multiple fields of production. In a production field there may be more than one reservoir. A reservoir is exploited by multiple wells, some for extraction and others for injection. The latter type of wells depend on the technology used to exploit the reservoir. The wells are connected to a collector that conducts the oil to a platform. The platforms can be connected to other platforms, or to a separator plant. The collectors are used for these connections. The separator plants are used to absorb oil on the water, and the gas on the oil. These products are stored in tanks. Oil, to be dispatched to other facilities of the oil chain. Gas, for reuse in injection, or to be dispatched to other facilities of the natural gas chain, and water, for reuse in injection, or to be processed in water treatment plants, for be re-injected into aquifers, or to be incorporated into the surface water flow system. According to the location of the reservoir, two types of oil extraction facilities should be considered. Offshore, when the exploitation platforms are in deep sea. Onshore, when the platforms are located inland. The objective of the modeling is to determine the most profitable way to exploit the oil field. For this it is necessary to coordinate hierarchical decisions over time, strategy, tactics and operation. One of the main costs is related to energy consumption. To calculate it is necessary to determine the energy consumption, to later multiply it by the energy price. The modeling that will be presented below, it is oriented for calculate the consumption of energy on shore facilities. The analysis of the price of energy is left aside, which is a very important problem, Given the multiple types of negotiations that can be carried out, this optimization of this process is called ETRM, Energy Trading and Risk Management, and is presented at another conference. Each well consists of two pipe segments, the well pipe and the flow conduction line. Between them is a shutoff valve that is used to control the flow rate. The part of the well that is inside the reservoir is called the wellhead. Energy consumption in an oil field can be divided into three phases. Energy consumed in the well during the production process, injecting or extracting materials. Energy consumed in the conduction of oil at surface level, in the gathering system of the extracted materials, and in the conduction of the materials to be injected, and energy consumed in industrial facilities processing the extracted materials. The determination of energy consumption in the hydraulic system of an oil field results from the integration of energy losses that occur in each well, energy losses in the gathering and distribution system. Power for the surface piping system is usually provided by a pumping station and a compressor. Consider all energy consumption in the field. Additionally, must be considered energy consumption in industrial facilities and in offices, buildings and the like. The model assumes that the problem of locating wells has already been solved previously, and they have been drilled and are ready to produce. Temporary closures are considered in order to control the production of the system. Together with the reservoir simulation models, OilPro can locate the wells that should be opened or closed to optimize production. The problem contemplates a planning horizon divided into several periods, each of them with a known demand, fluctuating in time, but which is assumed constant within each period. It is considered the decrease in pressure at the mouth of each well due to extraction, and pressure recovery, when the production of this is stopped. Pressure drop restrictions are included, in well pipes, and collector pipes, that interconnect wells to platforms and platforms with each other. The inputs of the system are flows of crude oil and/or gas, coming from the reservoir under specific conditions of physical-chemical composition, which enter the system through several wells, and the outputs are independent flows for each of the products extracted from the reservoir to be stored and subsequently delivered to the respective transport networks. Delivered directly to the auxiliary services plant associated with the production system, and/or be discarded, in the case of gas flaring. The relationships that determine the production behavior of a reservoir are pressure, G or gas-to-oil ratio, and W or water-to-oil ratio. G or and W or pressure are nonlinear functions of cumulative oil production. Linear piecewise interpolation may be used to model nonlinearities from a set of data obtained from reservoir simulations. The actual ratios for pressure, G or and W or, are taken as functions of the initial pressure, physical properties of gases, and gas mixtures, represented in phase diagrams, which characterize the state of matter, under specific conditions of pressure, volume, and temperature of the oil and the oil initial volume. The reservoir pressure function is a nonlinear function of accumulated production. The variables uses in the modeling are, the index k is associated with the interval in the approximate function linearly. PdYt, Y pressure in reservoir Y at the end of period T. P Y cumulative production in reservoir Y up to period T. T, Y, K variable that indicates the interval K of the curve in which the reservoir Y is, at the end of period T. The objective function must involve, in one way or another, the total extraction of oil from the reservoir. With respect to this behavior, it has the curvature of the function as nonconvex, and therefore accelerate the speed of oil extraction, leads to smaller volumes to extract. This behavior complicates optimization algorithms, by turning the problem into a nonlinear nonconvex problem, the solution of which requires solvers for global optimization. To address this problem, the nonlinear function can be linearized using a piecewise linear approximation. Given the nonconvex character of the function, it will be necessary to include binary variables to ensure the consistency of the representation. Associated gas production. In an oil and gas reservoir, the proportion of gas that is produced associated with oil, or GOR, varies with the accumulated production in a nonlinear way. Although gas has demand and a market value, The amount of gas produced in oil fields must be controlled, the production costs of the system are restrictive, and therefore only a gas-oil ratio can be extracted, no higher than a limit established by economic considerations. The gas can be used for both injection and power generation, and additionally for sale, after being properly treated. As in the case of the reservoir pressure, this behavior complicates optimization algorithms, by turning the problem into a nonlinear non-convex problem. To address this problem, the nonlinear function can be linearized using a piecewise linear approximation. Given the non-convex character of the function, it will be necessary to include binary variables to ensure the consistency of the representation. Water production. On the other hand, the water produced together with the oil may be used in the production system, either for injection into the reservoir, or retreatment the water to take it back to an aquifer. The WR must be restricted to prevent its excessive production. The form of the WR function is not known a priori, but can be established by field data and/or reservoir simulations. The following graph summarizes the pressure and flow dynamics model used, related to oil production wells. When the well is operating, the pressure loss is proportional to the amount of oil extracted by the well. This pressure loss in the well is linked to the variable dppTW. The operation of the well is modeled by the binary variable OPO-TW, that is, 1 when the well is operating, and 0 otherwise. When the well does not produce, the pressure at the wellhead increases according to the duration of the non-operation period of the well, until the maximum level of pressure recovery is reached. This pressure gain in the well is linked to the variable IPPTW. Primary recovery, mechanical pumping. This technique lifts crude oil from the wellhead to the surface, using mechanical energy. It is a simple, efficient and easy technique for operating wells. With the mechanical pumping, it is possible to pump from very low pressure wells. To maximize the rate of oil production, it is applicable to narrow holes, multiple well terminations and high temperature and viscous oils. The system is also easy to switch in the wells with minimal cost. The major disadvantages of mechanical pumping include excessive friction in curved, deviated holes, low efficiency in gasified wells, limited length due to rotor capacity. It is prohibitive for offshore operations. The flow extracted from wells is calculated according to the additional pressure generated by the pump system. The variable VBOM-TW controls the mechanical pump and corresponds to the rotational speed in RPM. Gas lift. The technique of continuous lifting by gas, or gas lift, is one of the most used methods around the world. Typically, high-pressure gas is continuously injected into the annular space of the well, through an injection valve, and flows into the well pipe to a point near the wellhead. The gas decreases the average density of the fluid within the pipeline, reducing the hydrostatic component of the pressure at the wellhead, and creating a pressure gradient, sufficient to produce flow from the reservoir to the surface facilities. Gas lift, or bubble pumps, use the artificial lift technique of raising a fluid, such as water or oil, by introducing bubbles of compressed air, water vapor, CO2, or other vaporous bubbles, into the outlet tube. This has the effect of reducing the hydrostatic pressure in the outlet tube, versus the hydrostatic pressure at the inlet side of the tube. The amount of gas to be injected to maximize oil production varies based on well conditions and geometries. Too much or too little injected gas will result in less than maximum production. Generally, the optimal amount of injected gas is determined by well tests, where the rate of injection is varied, and oil production is measured. Alternatively, mathematical models can be used to estimate the optimum gas injection rate. Such models offer significant economic benefit, since they allow one to simulate the performance of an actual, or planned, gas-lifted well, using a digital replica of the well. The ratio of gas injection rate in gas lift operations to outlet rate expresses the response of an oil production well to gas injection. As the injection rate increases, the production rate increases to a maximum value, beyond which the energy losses incurred by fluid friction in the production columns exceed the decline of hydrostatic pressure, forcing the rate of production to decline. It should be noted that production only occurs if the gas lift rate is above a kickoff rate, which is typical of mature fields, or can be imposed to ensure stability in production. As in the cases of nonlinearities mentioned above, in the same way, the injection-production relationship is established by linear interpolation to pieces, from a set of data obtained from simulations of the reservoir. Although the gas is recovered from the oil at a later separation stage, the process requires energy to drive a compressor, to raise the pressure of the gas, to a level where it can be re-injected. The oilfield infrastructure produced using gas lift technology consists of an injection gas collection system, which includes a compressor, and a system for collecting crude oil, mixed with gas and other materials, consisting of the piping system, separation unit, and material storage tanks. Electrosubmersible pumps are a highly efficient artificial lift method for well operation. They can obtain better productivity even than mechanical pumps, and highly productive and deeper reservoirs. They are easy to install and operate, and their lifting costs are generally low. But it also has some limitations. It is completely dependent on the availability of high voltage electricity. It is not designed to withstand high temperatures, and its installation and repair are expensive. Unlike positive displacement pumps, electrosubmersible pumps, which are multi-stage centrifugal pumps, do not displace a fixed amount of fluid, but create a relatively constant pressure increase for the flow. In this way, the outflow rate will vary depending on the pressure on the moving flow, exerted by the duct walls. Conventional controllers, which regulate the current delivered to the pump, offer pumping at a fixed speed and at a fixed flow rate. To overcome this limitation, there are variable speed controllers, which allow the frequency of the electric current to vary, and with it the production of the well. The pressure increase is usually expressed as the pumping height, or as the flow height produced, defining the pressure differential created that the pump could offer. The flow extracted from wells is calculated according to the well pump suction pressure in the well. The variable PSB/TW pressure in the well W and psi. The use of mechanical pumps is not feasible in deep or deviated wells, due to the weight, or the great magnitude of the friction that occurs. A positive displacement pump, that can be used in these applications, is the hydraulic piston pump. This pump consists of an engine, with a reciprocating piston motor, driven by a fluid. Generally, it can be used in low API oil gravity wells, and in wells with high paraffin contents. The high-pressure fluid driving the engine is injected from the surface, and is either returned to the surface through another pipe, or mixed with the fluid produced in the production pipeline. Water or oil can be used as propulsion fluid. Hydraulic piston pumping systems can lift large volumes of liquid from a great depth. The energy source can be natural gas or electricity. It can also be applied to wells of different terminations, and offshore operations. Because the pump and pistons of the motor are directly connected, the volumetric flow rates in the pump and the motor are related through a simple linear equation. The flow extracted from wells is calculated according to the flow rate of the propulsion fluid of the well W in period T. The variable QFP/TW rate is measured in barrels per day. Secondary recovery, gas and/or water injection. The injection of water or gas through of injection wells produces a dynamic increase in the pressure of the reservoir, with which it is intended to maintain, or to increase, the productivity of the producing wells. This process is called secondary recovery. This type of recovery involves simulating the process of managing of the impact of the resource being injected, natural gas or water, in the reservoir. This entails the need to link the optimization model with the simulation reservoir model. The modeling is fundamentally based on the dynamic pressure balance in the reservoir. It is assumed that the pressure throughout the reservoir remains uniform. This must be validated for each reservoir. Another main hypothesis is that the injection actually during the T period affects the pressure conditions at the beginning of the T+1 period. The parameters coming from the simulation model are FPIG/TW representing the pressure factor per unit of gas injection into the well W, and FP/TW representing the pressure factor per unit of water injection into the well W. The impact of all wells linearly affects the pressure in the reservoir. Then, the resulting pressure is the sum of the impacts of all the wells that inject gas or water into the reservoir. The control variables are GIPTW gas injected into the well W during period T. IPTW water injected into the well W during period T. And the state variable is PDY/TY reservoir pressure Y at the beginning of period T. Tertiary recovery. Enhanced oil recovery, EOR, also called tertiary recovery, is the extraction of crude oil from an oil field that cannot be extracted otherwise. EOR can extract 30% to 60% or more of a reservoir's oil, compared to 20% to 40% using primary and secondary recovery. According to the U.S. Department of Energy, carbon dioxide and water are injected along with one of three EOR techniques: thermal injection, gas injection, chemical injection. Microbial enhanced oil recovery, MEOR, is a biological-based technology consisting in manipulating function or structure, or both, of microbial environments existing in oil reservoir. Since tertiary recovery is an injection process, which affects the entire reservoir, the principles for its mathematical modeling are like those of secondary recovery. From the point of view of optimizing the use of resources using an injection, the optimization model must include the management of the resource that is being injected, which may be produced by the oil field, or must be purchased to an outside source. Flow in the hydraulic system that consists of the wells plus the surface system. The injection of water or gas into the injection wells produces an increase in the dynamic pressure of the reservoir, with which it is intended to maintain, or to increase the productivity of the producing wells. This type of recovery involves simulating the process of managing the resource being injected, gas or water. For the modeling of the hydraulic system, reservoir plus surface facilities, it is assumed that the production of a well remains constant during each period, and that its production capacity is restricted by several factors. Behavior of the pressure at the wellhead with respect to the reservoir. Characteristics of the well pipe. Features of the pipe of the collectors. Reservoir dynamics, energy conservation, and conservation of matter. Pressure and flow modeling in hydraulic system for oil production must be divided into two large parts: the energy consumed in the wells, and the energy consumed in the piping system. Each of the above parts requires specialized modeling equations. The mathematical modeling of this flow system, which we will call surface flow, involves: first, it takes as an entry point the pressure at the wellhead, which depends on the reservoir pressure and the increase in pressures that may have been generated by primary recovery technologies, different from natural recovery. These technologies are mechanical pumping, gas lift, pumping by electrosubmersible pump, and pumping by hydraulic pump. For natural recovery and for secondary recovery, the reference is reservoir pressure. In this way, the reservoir is linked to the surface pipe system. Second, pressure losses in the well pipe are calculated, based on the characteristics and equipment of the well. Third, at the outlet of the well, the outlet pressure must be equal to the pressure entering the pipe. Fourth, in each section of the piping system, pressure losses are calculated, based on the characteristics and equipment of the section. Following the principles expressed above, a system of equations is constructed that faithfully represents the decision-making process regarding the functioning of the field. The main decisions, for each period of the planning horizon, are: to operate or not to operate the well, flow in each production well, flow in each injection well, flow in each section of the pipe, engine speed, or pressure, of the pumps involved in the recovery process. The main characteristics of the equations are explained below. The fundamental variables of well modeling are QPOTW flow rate of fluids extracted from well W during period T, and POTW pressure of fluids extracted from well W during period T, at surface level. The pressure variable of the fluids in the reservoir, P and TW, determines the value of the pressure at the exit of the well, subtracting the losses in the well pipe. The equation that relates the pressure in the reservoir to the pressure at the end of the well depends on each recovery technology. An example is presented in the image. The operation of the well determines the change of pressure in the reservoir at the access point of the well. The fundamental variable is QPOT, W, that is a binary variable that determines whether the well W is operating, or if it is stopped, during period T. Considering the operation of the well, the equation of pressure change in the reservoir must be defined. If the well is stopped, the pressure increase will be IPPTW. If it is operating, the decrement will be DPPTW. Based on this equation, a dynamic equation is formulated for the pressure in the wellhead, for its variations throughout the planning period. To handle these types of constraints, it is appropriate to consider the use of disjunctive programming. This topic is discussed in detail at large-scale optimization conferences. The fundamental variables for the simulation of a pipe section are C and Ti pressure at inlet of pipe I during period T. C out T, I pressure at the exit of pipe I during period T. These variables are linked by the equation of pressure continuity, or energy. Finally, the well system is linked to the piping system through the equation that indicates that the pressure at the end of the well must be equal to the pressure at the inlet of pipe I. This implies that P out TW must be equal to C in Ti, where I is the section where well W is connected. In this way, we have a model for the optimization, at a detailed level, of the entire hydraulic system of the oil field, chained with the oil recovery model of the reservoir, considering multiple technologies. The following hypotheses are made with respect to product handling. All crude oil produced will be sent to another link in the oil chain through the oil and gas transportation system. 3 possibilities are assumed to produce gas depending on the field from which it comes. Associated gas in injection wells, associated gas in wells without injection, and free gas. The assumptions are: in the fields with injection a capacity, it is assumed that limits the amount of gas that can be injected. This is done by means of a unit of the service plant. In fields that produce associated gas, it is assumed that the amount of gas produced is known, as a function of the crude oil extracted. In fields that produce free gas, the continuity equation is included in reservoir reserves. In those that produce associated gas, it is not included. The gas is sent to another link in the gas chain via the gas transport system. It is possible to use gas to provide the energy needed to extract the oil. The water balance is not modeled in the system, only the quantity supplied is modeled. When water is the product that is injected, modeling of the final disposal of the water resource must be included. The image presents the link of the oil production system with the industrial services plant, which must provide all the final processing services in order to dispatch the oil and/or gas to the clients. The equations representing this system are assumed linear and summarized in matter balance equations and energy balance equations. The diagram presents the main flow variables of the model, which relate the production system to the industrial services plant. The suggested objective function is to maximize the net present value of the oilfield operation. Energy is one of the most important inputs. The presented model focuses on the calculation of this component of the objective function. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.